It's in the.
Something to do. Yeah, I was embarrassed. Now I'm involved in a program. That makes my pocket before I live. I'm doing AD for that. Memorial Day.
17.
Yeah, I was trying to get this. Why is it saying video is private? Huh.
Yeah.
Mary must have had something.
All right, well, I'll start recording it on here anyway.
Yeah.
I have just the Herald steps on the morning. I was getting ready and they started listing road closures.
All right. YouTube, good. All right, let's get started. I want to welcome everyone to the May 2024 meeting of the Mid-Atlantic Amateur Radio Club. We are trying something new. We're going to see if we are online. So let's see if people online say hello.
Anybody there?
Probably nobody's watching right now because I haven't publicized it, but the recording will be out there eventually. So people in the future can see us there. All right, so I'm Jeremy Carlo, N2ZLQ club president. So as we normally do, we'll go around the room.
I'm Jesse, KC3YBW.
Brian, AA3BK. AA3ZQF.
Jeff, WA3RIZ.
Bob N3KIZ.
Michael and 34MR.
MS3PS.
Alan, AB3FM.
Karen, Hey, I know what KC3ACM.
And I'm Ron, KC3APO.
And Bill, I'm KC3OUIS.
All right, welcome everyone. Thanks for coming, Bill. All right, so let's see. Let's go through a couple of upcoming things. We do have field day coming up in just a few short weeks. So Jim is not here tonight. He's sailing the 7 seas. So let's see. So a little update on field day. So we are planning to be at the Lower Providence Fire Department as we usually are. I think we're planning to operate 3 Alpha as we usually do. We've got our 3 club radios now and 3 antennas, so that'll keep us going pretty well. The Scouts Merit Badge session planning is underway. We've already got over 20 people registered for it.
And 3 laptops to go with 3 links.
And 3 laptops to go with 3 radios. And a generator. We got everything we need. We got over 20 scouts registered. Hopefully we'll get a little bit of help with folks who want to help the scouts on air making contacts. Would anyone be willing to help out with that? Between around 3 and 5 p.m.
At field day?
At field day.
They're coming to our site?
Yeah. Yeah, so we're gonna have 2 sessions on Zoom where we'll cover a lot of the introductory material. Then they'll come in on field day. We'll have a little bit more material for them. And then they get on the air and make contacts. So that'll primarily. What's that?
You have to do the workbooks.
Yeah, and do the workbooks, yes.
Then we final.
Yeah, so between about 3 and 5, I think that'll be the main hour that we're getting all the scouts through, doing all of that. And is there anything else in terms of field day that we need to know about? I think that's about it. So we will have a planning meeting for field day. That'll be, was it June 18th or something like that? It's Tuesday before field day, and that'll be on Zoom. So don't come out here. That'll be just on Zoom. Let's see, Hamfest. Bob, you want to give an update? We come up front and he'll be on camera. And public service too.
Yeah, I can do both actually.
Double pay.
I'd like to do public service first.
Either one.
Well, we had a public service event this past Monday. It was to help out the Radnor Memorial Day Parade. We had, it turned out that it didn't rain on us anyway. It rained later in the day, but it turned out to be a pretty nice day for a parade. And parade went pretty well. And we had 4 club members help out with the parade. And they were Dick, K3ITH, Jeremy, N2ZLQ, and Jeff, WA3RIZ. So let's get these guys big. And so anyway, yeah, it went well. And so on to Hamfest. Yes, we are going to have a Hamfest on Sunday, August 11th. And the setup day is Saturday, August the 10th. And in preparation for the Hamfest, we're trying to get Hamfest flyers out to all the other Hamfests in the areas, figuring that people who go to Hamfest will come to our Hamfest. And so anyway, there's a number of Hamfests in the area. A couple of them have already taken place, like Warminster was back in the early May, and a couple others last weekend. I was able to get flyers to the Pare Spring Hamfest. It's up in what's it? It's near Paramus, New Jersey. And we got about probably a little over 100, between 100 and 200 flyers handed out there. The next Hamfest that's coming up is this Saturday, June the 1st. It's the MARC Hamfest, the Ocean Monmouth Radio Club, Amateur Radio Club's Hamfest, and that's in Spring Lake Heights, New Jersey. For all these, we would really like to have people help take the Hamfest flyers to these Hamfests. So that was coming up this Saturday. Then we have another one, the Bloomsburg Hamfest. That's Saturday, June the 15th. It's in Lime Ridge, PA. Then we have on Sunday, June 16th, that weekend's a doubleheader. There's one in the Baltimore Amateur Radio Club's Hamfest in Upper Cove, Maryland. And then on June 29th, Saturday, June 29th, it's the Raritan Valley Amateur Radio Club's Hamfest in Piscataway, New Jersey. And then we get to July 6th as of course, the Harrisburg Firecracker Hamfest. That's in Harrisburg. And on the that's Saturday, and then on Sunday is the Murgas Hamfest. And that's up in Plains, PA. It's up near Scranton, yes. That's July the 7th. Then there's possibly one for the New Jersey Antique Radio Club. They're having a Hamfest on Sunday, July the 14th in Wall, New Jersey. And I think there might actually be another Hamfest somewhere in there. It's I couldn't find the flyer, but I think there might be another one coming up. And of course, the really big Hamfests in our area, I guess, aside from ours, is the Sussex Hamfest. And that's the let's see, was it? Don't say what club it is. I guess it's the Sussex County Amateur Radio Club. And that's Sunday, July 14th, and that's in Augusta, Georgia, or Augusta, New Jersey, rather.
I'll go with the club will pay.
Yeah, we probably don't need to go to New Jersey or Georgia, I guess. But anyway, there's Sussex, and then the weekend before our Hamfest is the Reading Radio Club's Hamfest. That's on August 3rd, and that's in Sinking Springs, PA. So we need help taking flyers to these Hamfests. That's what you can do like prior to the Hamfest if you want to help out. And then of course at the Hamfest, our setup day, there'll be lots to do. We're going to start setting up at noontime at the Pemberton Fire Company. And then of course we need help on the day of. We need people to sell tickets early in the morning, people to tear down tables and stuff, you know, and late at the end of the Hamfest. Lots of stuff in between. We need, especially, I think we need help with the tailgate field. That's typically been a weak spot. We need help setting up the tailgate field in the morning of the Hamfest. So if anybody wants to let me know what they would like to do to help, please feel free to let me know. So.
Well, I took over from Rich about the door prizes. I'm pursuing that. I hit the first round and I'm going to start some other rounds.
Okay, great. That's super.
We've always done that testing session.
Yes, we'll have VE testing session at the Ham Fest. So
I have not gotten any advanced
requests, yeah,
registrations. But it's
that's
kind of early.
early still, yeah.
We don't have a regular VE testing session.
No. We normally would have one on the first Saturday of that month, but we moved it to the Fest.
See, we do have a breakfast coming up on Saturday. Ned, did you want to give a quick plug?
We have breakfast coming up on Saturday.
What's the most important thing to know about it?
Breakfast on cue. If you've never been to a MARC breakfast before, and if you check in on 06 or 13, talk in on the way in, or
We're on Fusion.
no.
Okay.
Well, or if somebody will verify, if another Fusion attendee who's there verifies that they checked in on Fusion, or teaches me how to check in on Fusion, that's very kind.
You have a Fusion radio,
I know,
Yeah.
Yeah, but they're different repeaters on different frequencies.
Yeah,
So you have to have two nets.
well, actually, some of us have been known to do that. But anyway, breakfast is on me. It's 9 o'clock at Andy's Diner on Ridge, technically that's Ridge Pike. Right off of the Blue Route, between the Blue Route and Butler Pike.
All right, thanks, Ned. But Dennis, technical services.
Rich, I put it in volunteer to accompany me to Newtown Square sometimes. We'll pick the hottest day if that room has air conditioning.
Always with this.
And the situation has been more than a year now, not running a power amplifier, we're running just the exciter, very low power. Nobody seems to complain, because basically nobody's on the air. But we'll go and fix the repeater in case I should somehow not be able to do that in the future, at least it'll be running again, okay, that's not.
Are you replacing the amp or?
I don't know what the problem is. Right now, I'm just running the exciter, we had a power supply was cycling back and forth over the year. So a lot of things are going through my fan panel, fan amp, fan power supply.
So this one will have it.
My focus, apparently, that's the easiest.
All right, thanks, Dennis. Does anyone else have anything for the club? All right, so let's here the here. Turn on screen sharing here. All right, so I'm pleased to introduce our this evening's invited speaker is Dr. Dylan Pare, KE0VIS. So Dylan's originally from Massachusetts, did his undergraduate work at UMass Lowell. Is that in physics or astronomy?
That was astronomy.
Astronomy, so on the dark side. Then he came over to the University of Iowa. Was that physics or astronomy?
That was physics.
All right, so he joined the winning team for physics. So he did his PhD at the University of Iowa, and that's where he got his zero call. And since then, he's been a postdoctoral researcher at Villanova University, working on radio astronomy, particularly the Galactic Center. So please join me in welcoming Dylan.
Thank you. So am I in a good
Yep.
spot over here, or do I need to be
Yeah, I think anywhere.
closer? Okay, awesome. I think it's updating on your screen, but not. But anyway, yeah, I'm Dylan, so I'm relatively new to the Pennsylvania area. I've been here about I guess close to 2 years now. But I'm originally from Massachusetts, so the East Coast feels like home to me, you know, regardless of it being a bit further south. Let me see if. Oh, yep, awesome. So yeah, my research is more on the radio astronomy side of things, but I've also done a little bit with ham radio. I haven't done as much with that as I would like. But I've been enjoying being involved with ham groups and doing the work I do. So today I'll be talking a bit about the radio astronomy side of things. I'll start with kind of where we are currently in radio astronomy, just showing some of the instruments we use to observe radio emission from the cosmos, and also some of the science we're able to do with the instruments we have. And then I'll also talk about kind of the history of radio astronomy, focusing most on how radio astronomy came to be in the early years of the field, which was around the 1930s, 1940s kind of period that it was first starting. And then at the end, I'll talk a bit about kind of the future prospects of what people will be doing in maybe the next few decades with the field. So yeah, I mean, I probably don't need to include this slide with this audience, but you know, we're looking at radiation from the radio wavelength range. That's higher, larger wavelengths than what we can see with our eyes. So optical is here, and then you have infrared, microwave radar. I also do some infrared research, but radio is what I'm talking about today. And for radio astronomy purposes, the radio range for in terms of frequency is generally considered like 3 kilohertz to about 900-ish gigahertz. There's some ambiguity there. But for radio astronomy, that's generally the range that people consider.
Did you mean 3 gigahertz?
Sorry?
Did you mean 3 gigahertz?
Oh, yeah, sorry, 3 gigahertz. That's a typo. Yeah. So that's generally the range that people consider in terms of the astronomy side of things. And so I'll talk a little bit about how we do this kind of research. So we use antenna, kind of similar to ham, but much larger in a lot of cases, not always. So this is a single dish, a single antenna that's used for radio research right now. And this is actually an instrument that Jeremy and I have both visited in West Virginia. It's called the Green Bank Telescope. And kind of the famous thing that a lot of people know about this is that when this was built, they established what's known as a radio quiet zone around the instrument, where basically you're not really allowed to do much with radio at all. You can't really transmit at all within, I forget what the mile range is. I want to say 15 miles of the instrument, something like that. You're not allowed to transmit. When you're really close to the antenna, you have to turn your cell phone off, so that can't even be emitting anything. So as you get closer to the dish, the requirements or restrictions become more severe.
Question?
Yeah.
For people who are just passing through, are there signs on the road that shut off your phone?
Yeah, if you're driving right by, they do have signs of like entering radio quiet zone, something like that. And they actually do have a truck that goes around and finds people who aren't complying with it. So yeah.
Well, the construction crews that use dynamite have such.
Yeah, I'm not sure how that works. I mean, they're not always observing. So my guess is, I don't know for sure, but my guess is if there's something like that, they have to work out a time when they can do it when it would be disruptive. Because they're doing maintenance on the machine every now and then, they're not always actually taking observations. So if it's in maintenance, you actually can go right up to the telescope with your phone on and do whatever you want. So they probably have to work something like that with the Green Bank Telescope.
There's a radio telescope with that InfoAge Museum in Wall. Yeah, it's functioning right now. As Elton.
Yeah.
Generally, it's full. Do you work with them?
I don't really work with them at all. Yeah, so I've done a little bit with this instrument. A lot of my research is on these other instruments I'll talk about later that are called interferometers. They use an array or a set of these dishes. So I'll be showing those a bit later. Yeah. Yeah.
Does this have to occur at night? I presume not.
No. So generally they observe 24/7. Again, there's some times where they're not for maintenance and whatnot, but they're a little bit affected by the atmosphere, right? Like poor weather conditions do crop up depending on the frequency you're using as well. That's more or less of an issue. But in general, you don't really care about whether it's daytime or night. You know, you get about the same quality for most things. So. Anything else?
So the radiation from the sun, you have a way to
Well,
That-
yeah, well, there's that. Yeah, if you look right at the sun, yeah, the sun is a big radio source, so yeah, for sure, that's a problem, but. If you're, this is in the daytime, right, they're probably taking up observations right now. As long as you're not pointed within about a degree of the sun, you're
Oh.
okay, cause it's very directional, the way they have these designed. This kind of dish you see here with the paraboloid shape helps you only get emission from the general direction of the sky you're looking at, and there's some scatter from the
So they
atmosphere.
suppress the lobes,
Say what?
you suppress the lobes,
So the side lobes, there's a software they use to kind of filter out noise like that. They do for some frequencies, they have like a modeling of the atmospheric emission that they kind of filter out as well. So yeah, what you get from this instrument is processed heavily before it becomes something the scientists can use, because they have a whole frequency, conversion as well. To kind of, they call it an intermediate frequency that they then do a lot of post processing on. And then that's kind of what you get out as a scientist at the back end, which you then use to make like radio images that we can look at with our eyes. So there's a whole number of steps for sure. So this is one kind of what's called single dish telescope, and people use this a lot to look at kind of large scale structures, like maybe entire galaxies or large clouds that you see within our galaxy. This is another example of a single dish telescope, so a single antenna. So this one is in Australia now. It's known as the Pare telescope. And you can kind of see the way it's angled. It's easier to see a bit of how this is designed. So you have the main dish here. That's kind of got this curved parabola shape that helps you direct the emission from the sky. This object up here, structure up here, is what's called the focuser. So the light is all directed from the dish to this focus, and then it's reflected back down into this kind of central instrument you can see here. And this is the receiver, where the light is actually taken in and processed and down converted, etc. So I have a little diagram talking a bit about this. I won't talk too much about it. So focus, like I said, is up here. They have these support legs that kind of hold it in place at where the light is focused to. For this particular instrument, they actually have an elevator here. So when there's a need for engineers to get up there to upgrade or fix the focus, you take an elevator up and just work there, yeah.
So it really is like an elevator.
Oh,
It's
yeah,
not
yeah,
like-
yeah.
It's not like an elevator.
Oh, no, exactly, yeah, this is for like maintenance crews to get up there or to like fix an issue that might have occurred or upgrade, exactly, yeah. Let's see, yeah, so as I was saying, this is kind of like, they call it the vertex, but that's where the instrument is that receives the light, called the receiver, and then processes a lot of what's received from the sky. This instrument is balanced with a counterweight that just makes it easier to move at different regions of the sky. And then what I kind of like about this instrument, and it's actually just built on top of this kind of house-like building. And so the actual control room is in this building down here. So they're just working right under this massive dish when they're taking the observations. And the track that it moves on, it's a little hard to see, but there's just a track that it rotates on at the top of this building here. So this instrument, kind of like the Green Bank, is in a very remote area. It doesn't have an official quiet zone like Green Bank, but when you go out to this thing, you're driving through, the Australian outback for hours and hours, and then you show up at this building in the middle of nowhere, and there's this massive dish rotating and taking observations. It's pretty cool. And your staff who are working these instruments are living there too, right? Can't really, usually they're on site or living very close to, yeah.
How do they calibrate to know where they're pointing?
Yeah, so there's a lot of software that goes into that when they're first building these instruments. The main way you do it is there are brighter sources in the sky, right? So I'll talk later about Cassiopeia A, which is one of the brighter extraterrestrial radio sources, the sun as well.
Okay.
So you can figure out, like, where the sun or Cassiopeia A should be from previous observations. So all this movement of the antenna is programmed, right? So you tell the instrument to program it to move to the location it should be. And then you take an observation, and based on what you receive, you can see if it's offset by some amount and add a correction to get it better aligned. And they also have a lot of sensors on the dishes that help them judge where they're looking at in the sky as well.
Well, I would expect the surface, the area is pretty well surveyed,
The area,
so you know where the. Well, I mean, you have to know where the antenna is,
yeah,
in order to point, right? So you have to, I assume you surveyed the area, so you have a good, that long.
oh, yeah, right, yeah, so the location on Earth, exactly.
And then the motors that move the dish, they must have sensors on
Yeah, right, like I was saying, the sensors.
it. And they get calibrated.
Yeah, and those are often updated or replaced as there are issues that come up. There's a lot of maintenance on these instruments to make sure they're as accurate as possible. Yeah.
Round figures, how much power does it take to operate one of those things?
That is something I don't know off the top of my head.
Are we talking 10 kilowatts, 20 kilowatts, 1 kilowatt?
I mean, I wanna say it's tens of kilowatts, that bulk.
It's not a
Ryan,
train.
That's not right.
Ryan, our Arecibo had a 100 kilowatt station on location.
Okay,
Just the power of the dish.
the power of the dish and all the equipment.
Yeah, cause it is a receiver, but you're still powering the equipment, like the
Computers,
processors,
electronics.
exactly, so, yeah.
So
Doesn't have much
100 kilowatts.
No, but you get full.
Yeah, I think Arecibo was a bit more energy intensive, so it's a bit of a larger dish. I think these are smaller than Arecibo, so I think they're a bit less energy intensive, but again, I'm not sure.
Well, Arecibo didn't move, it was only the
Yeah, but you were still powering the electronics. Yeah, I'm not sure how the energy scale really.
well, it's all the computers and everything,
The
Yes.
radio unit would be the least evil parts.
Mhm.
It's all the other crap.
air conditioners.
Oh, yeah.
Yeah,
So, I'm really demonstrate my lack of astronomical knowledge here, but. It was a very powerful earthquake, when they're manic, that tend to change. The axis of rotation of the earth minutely. Does that affect this in any way, in terms of calibration?
not really. So the nice thing about radio is you can actually use radio to do your own astrometry, that's the term, right? I think it is where you measure the properties of like the local geography and variations therein. So you can actually use instruments like this to track those changes. I forget the exact process for doing so, but they're able to calculate if there was a change because of that, they're able to calculate it and correct it for it.
Sources, standard sources.
Okay, so a lot of research or science is done with just these single antenna. But what you can do is you can combine sets of antenna together, and that gives you sensitivity to smaller structures, like you can look at individual stars that emit radio signals, for example, and objects like that. And this is kind of more of what I use for my research. I use these kind of arrays of antennas for most of my work. And so this is a picture here of an array that's in South Africa. It's called Meerkat. And you can see it's built up of a set of pretty much identically designed antennas. So they all have the same individual antenna sizes and the same kind of electronics in each of these. And you point all of the antennas at the same source and take an observation. And then they have correlators that combine the signals from each antenna for the scientists to then use and create an image from. This is another example of this kind of array setup. This one is known as ALMA, the Atacama large millimeter / submillimeter array. And this is in Chile. ALMA is probably the one I use most often for what I do. And what's nice is it's on the Atacama plain, so very high up. So even though you're not affected much by the atmosphere and the radio, over here, there's not really any water vapor at all, and you're pretty high elevation. I think it's like 6,500 feet above sea level. So you're really not getting any kind of atmospheric effect most of the year. Yeah.
I see one antenna, is that under?
Yeah, I was
maintenance?
just gonna say, right, so, these antennas, so the ones I showed before Meerkat, these ones are stuck in their position, so they stay at each of these locations on the earth and just rotate, move around the sky. But with Alma, they're actually able to move to different locations, so you can see some of these bases are unoccupied. They actually have a machine that can pick up a whole antenna and move it to a new location. And the reason you would do that is, the more spread out the antenna are geographically, like the longer distance there is between them, you're able to resolve more extended or more compact sources. So if you want to say look at a star, for example, you want to use a more extended array. So you want these antennas spaced further apart. And so Alma can actually do that for you, where they move the antenna apart. I think about twice a year, they do a maintenance or a transition period where they move these antennas into preset configurations. I think there's like 8 or 9 for Alma configurations. And so basically, depending on the science you're doing, you would use like one or more, like a few of these configurations that are ideal for what you're trying to do. So this one allows you to do that. And this array as well, that's called the Very Large Array, very creative name, VLA. This one is actually in the United States in New Mexico. This also allows these antennae to move. They're on this kind of Y, these 3 tracks that are shaped like a Y. So you can actually move these antennas. There are actually, these are on train tracks, so you actually can move these like further apart or closer together along these tracks based on what you want to observe. So again, they have these cycles where every few months they move them further or closer apart, and depending on your science, you would use one of these configurations. I also use the VLA for a lot of the kind of work I'll do, which I'll talk about in a little bit.
The VLA is basically the grandfather of everything else, right?
Yeah, so VLA predates like Alma exactly and
I guess
Meerkat.
I'll see the first.
Right. So for single dish, there were a few that were earlier, but in terms of like these kind of arrays working together, right? VLA is kind of the first one. And as I'll talk about at the end, they're actually thinking about upgrading VLA, yeah.
The kind of silly question, but the movie Contact was about, I think it was about this array.
Oh, yeah.
And did they actually use this array in the movie, or did they build a
Yeah, so like the signal that I forget the actress's name that she's listening to. Yeah, Jodie Foster, yeah, that's not a real radio signal. You can't really listen to them like she was doing. Yeah. But they did actually go out to the VLA site and shot a few scenes there. Yeah, exactly. So that was pretty cool. They actually have a copy of the Contact movie in the control room. So of course you got it, right? Yeah. So those are kind of like the main instruments. There's a lot of other ones, single dish, etc., that people use, but I just wanted to highlight some of what's currently used. And I'll just talk briefly about some of what can be observed with these instruments. So I'll talk more about what this is later, but basically this kind of ellipse here is like a projection of the whole sky. So you're kind of looking at the whole sky in this weird projected view. And in the radio, there's kind of this constant low level signal that you're seeing. It kind of comes off as a hiss in certain observations. And early on, as I'll talk about later, when radio astronomy was first being established, people were trying to figure out why there was this low level radio signal everywhere they would point a telescope to. And eventually what we think is going on, right? It's always developing, right? So the real answer could be different, but what we think this signal is it's remnant light from an early age of the universe, when the universe was a lot hotter, brighter, and basically everywhere in the universe was emitting. And so that period is thought to be about 300 to 400,000 years after the Big Bang, so almost 13 million or billion years ago, rather 13 billion years ago. So this is basically the furthest back in time that we can see is this radio signal, and astronomers use the signal, which is known as the cosmic microwave background, to try and test for theories of how our universe went from this hot, more compact state to this larger universe with galaxies and what we have now. So this was a very important finding from radio astronomy that people are still studying and improving our understanding of to this day. There's an entire collaboration devoted to that. But you can also look, closer by to distant galaxies or nearby galaxies. So in the center here, this is a galaxy in optical light. So what we would see with our eyes here in the central region. But in the radio, you've got these large like plumes or jets that are much larger than the galaxies themselves, right? And astronomers realized that these were energetic kind of like outflows or bursts from these black holes that are found at the centers of each of these galaxies. The black holes kind of accelerate matter to such a speed that they're launched far away from the galaxies and are still emitting this high energy radio light that we see. And people study these jets to get a sense of what's going on in the centers of these galaxies because they're far enough away that we can't really observe what's going on in the center, right? So they need to look at these other objects and make inferences about what's going on. This is just another example where the galaxy is quite compact, and then you have these much larger jets in the radio that people study. And then last kind of example is looking at our own galaxy. So there's this spectral line, a hydrogen line known as the 21 centimeter line. So that's the wavelength it emits. It's about 14, 18 or so megahertz is the frequency. So this H1 line happens to trace a lot of the gas and dust that's in our galaxy. So this is again a projection of the full sky, like with the CMB that I showed earlier. So what you're seeing here in this kind of horizontal line, this is actually the galactic disk of the Milky Way. So you're able to see the dust and gas emission from our own galaxy, and using observations like this, astronomers have put together models of how our galaxy might be shaped, which is something that's kind of difficult to do because we're embedded within the galaxy, right? So this is just an example of a kind of model that astronomers have put together based on these kinds of observations. There's always disagreements and updates to it, but our sense is that we have these spiral arms in the sun. It might be a little difficult to see, but the sun is located here between these two spiral arms. And then the center of the galaxy is over here. So we're kind of closer to the edge of the galaxy than the center, at least to our understanding. And then last thing before going into the history, this is our image of the center of the galaxy. This was made using the MARC telescope I showed earlier, the first of those arrays. And you can see how much we're able to see of our own galaxy in the radio with all these different structures. Like there's these thread-like structures that trace magnetic fields. There are these kind of shell-like structures which are remnants of stars that have exploded. So the center of our galaxy is the kind of research I do. So because we're looking at an object closer by, we like to use those kinds of arrays I was talking about that give you better resolution and let you actually look at these kinds of thread structures and actually pick out like how they vary. So in terms of the current state, that's what I was going to talk about. And so now I'll go over kind of a brief history of the field. But were there any questions on the kind of current state stuff before I go to the next topic?
Is our wireless world impacting radio astronomy?
Yeah. So it's not as bad as it could be because a lot of the high-end instruments are in remote areas, right? Like the VLA as well is in the middle of nowhere in New Mexico. But even there, you're still impacted by wireless signals. So they have a lot of software now that they've designed to try and remove these kinds of signals. And a lot of times they show up as these spikes at particular frequencies, right? So those are pretty well characterized most of the time, and you can remove them, but as technology continues to advance and as we get more and more, urbanized, it's going to become more of an issue. So there's a lot of pressure right now to get some of the newer instruments that are being developed, which I'll talk about at the end, to have kind of radio quiet zones, kind of like what the Green Bank has. Just to make it a better observing region for radio. But obviously, locally that can be complicated with local communities and figuring out how to negotiate all of that. Yeah.
I'm kind of under the impression that parabolic dish antennas, the gain of the antenna varies with frequency due to the size for particular size of antenna. But what like for these single, like Green Bank one or some of the other single ones, like that are really big, what's like a typical gain range that you said it went from 3 gigahertz to 900, so there should be like a range, I would think, gain.
Well, yeah, so in terms of exact values, I don't really have that off the top of my head, but one way they're able to kind of compensate for that is not every one of these instruments operates over that full range, right? So for the VLA, for example, that actually only goes from like the 3 gigahertz to about 50 gigahertz, so the lower frequency range. Whereas OMA is more like the hundreds of gigahertz. So the way they design those antennas and all of the instrumentation that goes into them are kind of optimized for these different frequency ranges, and that's part of how they're able to get around that instrument, is they're only looking at part of the radio regime. And you have a question?
No, I had a vision of somebody plugging in a wall wart to charge their cell phone and take it down.
I'll do a brief aside based on that, but this instrument that I showed earlier, the Parks one, this one is the instrument that actually found the pulsars that people study now. They're like these variable sources that you see in the radio. But when they were kind of first discovering these objects, they kept seeing this pulsar signal that just seemed to happen at random times, like it wasn't associated with a specific part of the sky or anything. And it just turned out that there was someone microwaving some food that was just in this. Actually, it wasn't in this building. It was nearby.
Sure.
But yeah. So whenever that person was microwaved, it would be the signal. It took them quite a while to figure that out, but they did eventually figure that out. And then they were like, "Yeah, we can't have microwaves within so much distance of the instrument." Yeah. Exactly.
Remember
So,
the
yeah,
microwave at Green Bank?
Sorry?
The microwave at Green Bank was inside
Oh,
the
that's
Pare
right.
cage.
Yeah. We did have a microwave there, but it was insulated. Yeah.
A big metal box grounded to get some rod or something outside.
Yeah, exactly. All right, so in terms of history, this field is actually pretty young. I would say it's probably the youngest field in astronomy. You could make the case that gravitational waves that are starting now is its own field, but I'm not so sure. So really, people kind of consider the start of radio to be around 1933. And this was when an engineer, Carl Jansky, was working at the Bell telephone labs, and he was basically tasked with evaluating why there was the static that was observed on transatlantic radio telephone lines. And he eventually identified that it wasn't from a terrestrial source, which is what everyone thought, but was actually coming from a particular location in the night sky. And so this is that source I mentioned earlier. It's called Cassiopeia A. And it's called that because it's located within the Cassiopeia constellation. So it's from this particular region of the night sky. He was able to use an instrument to identify roughly where this was. And this was kind of the first detection of an extraterrestrial source of radio emission. So that's kind of considered the start of the field, but the astronomy community didn't really appreciate that discovery. It was just kind of thought of as like this weird kind of one-off detection, right? So for about a decade, no one really made use of that to do anything with the fact that there might be these radio signals until Grote Reber came along in the 1940s. And he got really interested. Jansky had published some papers back in the day, and he read those papers and was really interested in the finding and wanted to see if he could discover more sources. So he actually built his own radio telescope just in his mom's, I think it was, backyard. And it's kind of funny at the time, airplanes were told to avoid that area in case like they didn't know what it was, so they didn't want the radio antenna to like mess up airplanes and stuff. So he, using his own telescope that he built, was able to confirm what Jansky found, and he also was the one who discovered that the sun emitted radio waves as well. And he was already an astronomer prior to this, so his discoveries were kind of more widely regarded, and people started looking at this in a bit more detail. And okay, I did include. So this is a picture of what he built. So he kind of built this in his own time with his own money, which is kind of crazy.
Pretty elaborate first.
Yeah, yeah.
Popular with the neighbors.
Oh, yeah. They were,
HOA.
yeah. Yeah, exactly, right.
Tell us for Channel 2.
So a lot of this stuff was kind of, the very, very first detections. But a lot of the technology that we use today is based on technology developed during World War II. So specifically, the improvements and upgrades that were made to radar and testing radar during the war were later applied and used for radio astronomy. And so I'll just highlight two of the people who were doing that kind of work during the war. There's James Stanley Hay. He was working in the UK, and he discovered that the radar systems there would fail because of sunspots. And so that was an interesting discovery, that they again thought that these radar failures were happening because of something the Germans were doing. And so they were trying to figure out what the Germans were doing to mess up their systems, and it just ended up being the sun. And so these results of his and the next guy I'll show weren't actually published until after the war, right? Because it was classified. So this kind of happened in kind of the earlier 1940s, but wasn't then accepted or more widely received until later in the decade. So it was really until like the late to mid 1940s that radio astronomy really started being viewed as a serious field, because you had what Jansky published a decade ago, what Reber was doing with his own instrument, and now Hay and a few others had started seeing other radio signals from outside of the Earth. And then I'll just show one other from around the World War II period, Bernard Lovell. He's pretty well known. He's often considered to be like the greatest radio astronomer of the 20th century. He was also working with radar systems during the war, but he encountered a different interference source, which were basically there are these particles that interact with the ionosphere. And so he identified that this was what was causing these weird noise signals he was seeing. And after the war, he actually ended up salvaging a lot of radar equipment that had gone unused, and started essentially his own research group at his university to follow up on this work and actually research what these particles were. And later on, he got funding to build the Lovell telescope, which is one of the kind of famous, historically famous radio instruments that's still, I think it's used mostly for outreach now, but it's still operational in the UK to this day. So these are kind of like the forefathers, I guess, of radio astronomy, like the really early period. I just wanted to show an image of, this is Jansky again, and this is the instrument he used at the Bell Labs to make the detection. He's got these strips of metal that kind of pick up the radio emission. He's got some electronics connected here to receive it, but he was only able to make a rough, with this instrument, he was only able to roughly determine where the source was, right? So follow-up observations later from like Grote Reber and others were able to pin down where exactly the source was. But I thought it was cool to kind of show, this is kind of the first radio telescope, right? Yeah.
One of the early slides
You mentioned the frequency range of modern study.
Yeah,
It's a pretty wide range. Back in the early days, surely they didn't get up into tens of gigahertz.
no. This was, yeah, back early on, this was like the single gigahertz range, right? I think maybe,
That was maybe 20 megahertz, wasn't it? Or there was a story that asked, why did you pick that frequency? It was because the length of the metal pieces was what was available in the hardware store.
well, right, yeah, so exactly, there were other limitations like that as well. I think Rote Reber, like with his instrument, I think he maybe got to 10 gigahertz, I think. But
Pretty impressive.
for building it himself, right? Yeah, exactly. And then I'll just briefly highlight one of the developments from later on. I already mentioned the cosmic microwave background, but I wanted to show the instrument that was actually used, that kind of first detected this hiss or signal everywhere. It was this horn instrument here that was originally at the Bell Telephone Labs. So this was a discovery made in 1965 by Panzias and Wilson using this horn, and actually one of the other reasons I mentioned it is Jeremy and I were able to see the horn because it's not used anymore, but it's still at the Green Bank telescope site. They have it still not really on display, just kind of.
Was it the Penzias horn that was there? I thought it was a different one.
I think I'm pretty sure.
This one was actually disassembled because it's at home down.
Okay,
We all shut down.
okay.
I think it was a Purcell horn.
Yeah, so there were a few of these horn type instruments that were made
But the
early.
quick story is that when this was used to communicate with the first satellites, Cellstar, and it was Echo satellite, the big balloon and all that. And they had a lot of background noise, so they spent like a couple of weeks, because they thought it was pitching inside the.
Yeah.
Constantly trying to move back.
Yeah, exactly, and they saw it wherever they looked, right?
So it wasn't really used for radio astronomy, it was basically.
Right, yeah. No, that's a good point, yeah. Okay, so there's a lot more I could say, yeah, this is the image again, this is our current image of the CME, this isn't what they saw back in the day, but. So this is a very kind of brief overview of some of the early stages of radio, but were there any other questions before talking a bit about kind of what we plan to do? Yeah.
Yeah, sorry, this is kind of a delayed question, but I think you had a diagram of like, I think it was the Milky Way projections of like wavelength and like temperature, I think it was,
Wavelength.
unless I just read that wrong.
This one? Yeah. Okay.
Frequency and temperature,
Yeah,
is there like a relationship between temperature and frequency, or like
Oh,
what's the reason
so-
for those being the
Yeah.
axes?
So there's a relation not between frequency and temperature, but as astronomers, we measure light, so the intensity of light. There is a relationship between the amount of light you receive and the brightness of the source, kind of dependent on the wavelength or frequency you're at. So in this particular plot, instead of just having brightness, they're expressing it as temperature, basically indicating that this region is brighter or hotter than this particular wavelength here. And this plot here is also in brightness, so this kind of center strip here is a higher temperature and therefore brighter than what you see like above and below.
Okay, thank you.
So the reason we've seen 3 peaks, those are Doppler shifted, right? So you're seeing different structures that are moving towards or away.
Yeah, exactly. So a lot of the work is done on this particular line, but you can look at some of the other Doppler shifts of the same line as well, depending on what you're doing. Yeah. So let me get back to where I was. Yeah, so I'll just talk briefly about some of like what the next 2-ish decades might look like for radio astronomy. I'll just highlight 2 of the new instruments that are being developed. They're actually both approved with funding from various governments, so they are being built. So this is actually the VLA I showed earlier in New Mexico. That's the central dot here. And what they're planning to do, this is an effort led by the United States, is to expand or upgrade the VLA. The new VLA will be called the Next Generation VLA. And what they're planning to do is add additional antenna at these red dots and purple dots here. So you can see the red dots are much further spaced out, like even going into neighboring states like Texas and Arizona. And the larger spacings again give you better resolutions, right? So you're able to look at even smaller scale structures, and I'll show some of what you might be able to achieve with these kinds of improvements. And then the purple dots are even higher or further spaced dishes. This allows you to do a method called VLBI, very large baseline interferometry, and people use that method to study structures like black holes that are kind of difficult to observe otherwise and have really small scale features. So these new red and purple antenna will greatly increase what the VLA can do and really allow us to make new discoveries. So I use the VLA currently. Once the NG VLA is fully built, I plan to use that. I think right now they're estimating that the NG VLA will be fully operational by like 2038, 39, something like that. So I guess 15-ish years from now. So I might still be up front.
Whereabouts was that, is that being built, down or area?
Oh, like where the antenna is actually being like constructed? Yeah, so they have it's not in the image I showed earlier, but at the VLA site, they actually have like a construction maintenance area. So they've built the prototype and that was approved on site there and then moved it to wherever it's going to be. I'm not sure if in the long term, like I think for the ones in red, they're gonna build them at the VLA and just transport them because they have trucks to do that. But for these further spaced antenna, especially like there's a few in Hawaii, right? I'm actually not sure what they're planning to do with that. Yeah, I meant to point that out specifically, but yeah, they do have a few they want to build in Hawaii. So I'm not sure if they're just gonna build them like on site, like near to those locations, and then just set them up there or transport them somehow. The purple dots are kind of like the 2040s, so I think they're still not sure how they're gonna do those. The red ones are kind of the ones they're working on setting up right now.
Question?
Yeah.
What's the practical limit? In terms of distance between two stations that you can run one of these baseline from?
If you're stuck on Earth, I guess you can go from one side to the other. You can do that, because then you correlate the signals later and can then combine them. They have software to do that. However, there are proposals to get space-based interferometers, so you could have much further distances based on that.
Yeah, and you wouldn't have the curvature.
Yeah, well, so they have ways of accounting for that though as well. So I didn't show it earlier, but this is not the first kind of VLBI system.
But I would think isn't there an issue with the time lag between when one, on the average of view of one and so you're not getting a simultaneous image.
Yeah, so this is why you need to correlate them. So you basically have the telescope set up to observe the source once it gets to a certain point above the horizon and starts taking observations of that source at that point. So each of these antenna will have its own data stream, basically. And then what the VLA does, for example, is all of the signals from these different antenna are then fed into a computer bank that correlates the signals and kind of aligns them based on common features. But then there's a lot of post-processing that's involved in making sure it's properly calibrated and aligned. And once all that's done, you then have a signal from all of your antenna that you can then work with to make an image.
But that assumes that in that time period between the first listen and the last listen, the object that you're studying is relatively stable.
Yep, it does. So, one other way, so basically there's multiple steps that go into calibrating signals. So on one hand, you do a correlation, but then on the other hand, what you do is, let's say you're observing a supernova or something. There are known sources in the night sky that are known to not vary, so their brightness is constant. So what you do is these antennas will alternate looking first at whatever you want to observe, and then they'll move to a source nearby that's known to be stable, so it doesn't have much of an adjustment to do. It'll take like a minute observation of that constant source, then go back to the target you're interested in, take more data, and then you compare the stabilities of your antennas with what you see for your target. So basically, any variation you see in the source that should have a constant emission, you know that variation is a noise source. So you can then correct for those sources of noise based on.
Yeah, I guess that puzzles me is, how do you distinguish a noise change from bona fide phenomenal change?
Well, so that's why you use these calibrators, because you assume, so like basically pick a source that's near your target so that the telescope can move quickly between the source and the calibrator. So you assume in like the minute difference that there is there, that the variation that you correct for is noise and not something buried in the source, because you have these small time delays.
Well, I can see between the sort of your target and the calibration.
Yep.
That there's a short time difference. And so you can,
Yeah,
you can put adjustment. But you've done now several minutes, maybe tens of minutes later, you've done the same thing with another stable source.
Nice.
And then when you compensate, after you do the compensation based on the calibration points, there could still be a residual difference that could either be some kind of noise in the object, or it could be some phenomenon.
Well, so
That might be it.
yeah, right, exactly, but the way we kind of try and account for that is we have all the antennas looking at the same calibrator. So even for VLBI, they're all looking at the same calibrator, because the distance is the distance in the sky. But the other way we kind of try and ensure that the calibrator is stable and not varying is there are focused observations of just the calibrator every few months, where you compare that calibrator to another calibrator.
I have no problem with the calibrator.
But maybe I'm not understanding the question.
Yeah, the question is, how do you distinguish between something real and interesting? You know, for example, the star is undergoing some kind of change rapidly on the order of minutes.
Yeah.
Like a supernova.
Yeah.
As opposed to there's noise in the reading itself.
Yeah, so this process that I'm explaining is or basically, so we're never 100% sure we've gotten rid of all noise, but this is our way of estimating the noise, right? So imagine you have a signal that is maybe decreasing with time, right?
Yeah, I understand what you're saying.
Yeah.
It seems to me that the bias in the methodology, that is, you're got a confirmation bias on noise that's allowing a phenomenon that might be interesting to slip.
Well, right, and so, I mean, that is a good point, and some of the other sources of noise that people thought were noise were actually discovered to be real detections. So those pulsars I was talking about earlier were first thought to be some weird instrumental thing. So yeah, you're right. One way that we can check for that is if we're looking in different regions of the sky and we see similar signals, but conditions maybe like in the atmosphere or locally are different, then that helps us identify maybe it's not a noise signal, but something. Yeah, exactly. So maybe that answers your question. Yeah. Okay. Yeah.
So, you also probably take those readings like once a month.
For the calibrator,
Well, not so much the calibration as well as whatever object it is you're observing, right? You don't do a single observation.
Right, that's true, yeah. So like, for example, like some of those galaxies I showed, right, with the jets, those have been observed many times by different astronomers, because people might have different science goals for those.
And how long does post-processing, how long does that post-processing take, or what does it involve?
Well, so there's right now it's all automated with banks of computers, and that's actually one of the challenges for instruments like this, is figuring out how to do that efficiently when you have 100+ antenna, something like that. But yeah, so there are these computationally sophisticated computers that do it all. Honestly, for radio astronomy, you get data sets that are maybe a few hundred gigabytes a lot of the time, so these are kind of big data sets. But the actual processing that the amount of time it takes for it to be processed and kind of ready for the scientists to look at is really not that long now. So for the VLA, my recent data set I got from that instrument, I got it early May, I think, this year, like May 3rd, something like that. And by May 10th, I was able to, it was ready for me to get from their data server. And that includes, they have engineers who kind of do a bit of a double check, so there's a bit of a human element to that too. So if that wasn't there, it'd probably be even faster.
There was, I believe it was on Netflix, a documentary, I think the title was called Black Holes. Yeah, you see it?
I actually know a few of the people who are in.
And they did that, I mean, they had to have antennas or arrays all over the world start simultaneously collecting data. And they brought all these hard drives together to a supercomputer.
Yeah, exactly.
They divided people into 5 groups of a few people to work independently on crunching the data to come up with a visualization of where the black hole was.
Yeah.
And surprisingly, they all came up with exactly the same thing, but it took them, I think, a few weeks maybe.
Yeah, so that was more complicated because the processing here, the antennas are identical.
Yeah.
With that instrument, they were combining signals from different antennas, so that's why it took them longer to do that, and they had to do it a lot more manually as well because of that, which is why they had the different groups making sure that they were. The idea was if they all calibrate correctly, we should get a consensus, which they were able to. Yeah. I should have shown that image of the black hole. That's a good one to show. I just didn't think of it preparing the talk yet. I'll just show one more. This is still a bit more preliminary, this instrument, but this is known as the square kilometer array. So this is an effort that's kind of led by Australia, but it's more of an international effort to get this machine going. And the way they're doing it is they're building a lot of precursor kind of instruments that will then ultimately be a part of this full square kilometer array instrument. And so the MARC array I showed earlier will be part of the square kilometer array. It's currently operating on its own, but that's one of the precursors. And so this will be one of the instruments that's kind of spread out around the world a little bit. I know there's a site that they're currently working on that will be in Australia. The MARC is in South Africa. So this again will have those larger distances between the antennas that let you get to higher resolution. And this is just kind of their artist depiction of a prototype of what the antennas will look like for this. So I just want to briefly say some of what you could do with these kinds of upgrades, why would we care to do it? What's exciting about having these upgraded telescopes? So I mentioned earlier that we don't currently have the resolution to observe what's in the centers of these galaxies. They're just too far away. With current instruments, we can't really see what's going on in the cores, how things might vary, what kind of structure is in that region. But we can with our own galaxy. This is another image of the center of our own galaxy. And so right now what we're doing, this is again kind of what I'm doing with my work as well, is we're looking at our own galaxy center and making inferences of okay, well, this might be how other galaxies in their cores behave. But with these new instruments, they'll be powerful enough with at least nearby galaxies to be able to probe right into the core and maybe even resolve the black holes, kind of like what was done with our own galaxy's black hole that you were talking about earlier. And then we'll be able to see are all of these core regions, do they behave the same? Are they different? And that will allow us to understand much more detail, like how galaxies formed, which is relevant to our own existence, because stars and planets form within galaxies. Yeah,
You mentioned resolution.
yeah.
Is it possible to categorize current and future resolution in so many arc seconds?
Yeah.
Is that a reasonable?
So, yeah. So let's say for ALMA, for example, which is kind of the ALMA has the best resolution you can get without doing the VLBI thing over the whole Earth. So ALMA, I think its best resolution is 0.001 arc seconds. So a pretty small angular distance. And that's really good for the galaxy, and you can do a lot of work on other galaxies as well, but there's limits to that. With the NGVLA, that will be 100 times improved, so like 1 micro arc second, something like that. So really, really fine scales. That's not good for all research or science you would do. There's some reason you want to have a low resolution to look at larger scales, but the kind of limit right now is that there's a lot of structures or objects we want to look at that we simply don't have a good enough like eyesight, if you would, to see. So just as one last example before I wrap up, one of the big questions is how are stars and planets formed? This is an instrument made by ALMA where they're looking at a star that's forming in the center here, and then all of this emission out here is dust, and you can see that there are these kind of dust lanes. These are actually planets that are being formed and are kind of sweeping up the dust that would be in these regions. But you can see like this resolution, like you can see a lot of detail, but it's still blurry and we're not really able to make out like where are those planets that are being formed, what their properties might be, etc. So instruments like the NGVLA will be able to give us much higher resolution pictures of these kinds of, they're called protoplanetary disks. And we can see like how are these planets sweeping up dust to form the kind of rocky planets like we are in on Earth, yeah.
So the dust bands are not actually emitting RF, right? Are they, or are they actually attenuating it?
Right.
Yeah.
So this central like it's not really a star, it's like a protostar. It is still starting to emit. And so what's happening is this is emitting and then the dust is reflecting it.
Okay, so it's that sort of attenuation.
Yeah.
By reflection.
Right, exactly. Yep. So yeah, that is what I had for today. Were there any other questions?
Yeah, as a researcher, I'm curious, so you've got some experiment in your mind. Do you just wait for somebody to give you data, that's general data, or do you go to one of these telescope operations and say, I want to study in that location for 3 hours?
So all of these instruments have what they call calls for proposals. So sometimes it's once a year, sometimes it's twice a year, depending on the instrument. But basically, if you have an idea, like for me, I would apply to VLA, for example. I think for them, it's January and June. They have deadlines to submit. And you basically have to write, it's like a 4-page, usually science case about why your observation is important. And then you need to indicate how much time. So these instruments are all oversubscribed. So the big competition is, 24 hours in a day, 365 days in a year, right? They can only do so much. So you need to justify, I wanted to use 20 hours to look at something. Why should they look at that versus anything else? And then once you've submitted that, there's usually a panel of other scientists who haven't submitted proposals who then basically rank the proposals based on like scientific merit and stuff like that. And then only the highest ranks are allowed.
When you say you might request 20 hours,
Yeah.
of course, the Earth is rotating in 20 hours. Are you like asking for like an hour slice over 20 days, or how's that work?
Right. So it depends on what you're looking at. Like if you're looking at variability, you might do a few minutes at a time.
Okay.
Other times you can do 3, 4, 5 hour blocks, and then you can then combine each block of 4 or 5, whatever, together at the end, yeah, exactly. Yeah,
What do these facilities charge to do that?
they're free, yeah, oh yeah. So it's a lot of these telescopes are manned or managed by federal organizations, so the Green Bank was managed by the NRAO, now it's managed by a different organization, but the VLA is managed by a federal organization called the National Radio Astronomy Observatory. They're also the organization that's upgrading the VLA. So they are the ones who operate the instruments, and it's essentially taxpayer funded, a portion of the taxpayer allocation sent to the sciences, some of which NRAO receives. So as a scientist, you're able to, you don't have to pay to use them. And even the general community can, for some of these instruments, at least you don't have to be a scientist to submit an observation proposal. There are citizen science projects that people do on these instruments and they get time to do them. So if anyone's interested, it's definitely open. Yeah.
I know that you probably already noted this, but in the beginning it says like 300 to 900 gigahertz.
Right.
So why is it that and not like lower frequency? Is that because of I guess like most of the radio waves are already on the earth or?
Well, it's as you change your wavelength frequency, you need to design your instruments in a different way in a lot of times. So the way infrared astronomers make observations uses very different systems than what you use in radio. So in the field of radio, the distinction has kind of become how the instruments or receivers or whatnot are actually designed, more so than what the frequency per se is.
Okay.
Yeah.
And so like would you get different data? Do you get different data by switching that?
Well, so yeah, in the sense that different objects emit at different frequencies, right? So if you look at a region of the sky in the optical, you know, you'd see like stars, galaxies, like what we see. But if you look at that same region in the radio, right, like I showed some of those plumes, you would see that, but not those galaxies necessarily. So you'd see different stuff like that.
Okay, thank you.
Yeah.
I'm way out of my element and Jeremy's probably gonna beat me down for this question.
I'll do that anyway.
Yeah,
Let's start now.
now I'm thinking, okay, so might you be looking at a specific time and a specific frequency or slice of frequencies?
Mm-hmm.
Could then there be other people using other slices at the same time, other frequency slices?
Oh, yeah.
I'm thinking of basically frequency domain multiplexing.
Yeah, right, so I mean, that's actually becoming an increasingly common utility, is you've got, you know, the instruments I was talking about are radio, but you've got infrared instruments, you've got UV, you've got X-ray. It basically pretty much every instrument now has their observations publicly available, like on an archive. So what's a lot of what's done now is how does this source vary in the infrared versus the radio? You can usually find an observation of that region of the sky that you can take from an infrared instrument. And then there is a lot of interesting science you can do about, you know, how does this source vary across such a large frequency based on that.
Jeremy knows, I'm picturing a waterfall. Okay, so
All different frequencies.
different slices of that. So it wasn't that bad a question.
No, that's good.
Yeah.
Well, usually you'd have a detector that would only be sensitive to a certain range, right?
Yeah, but you know, using different instruments, right?
Yeah.
And then, you know-
once you down convert, you're putting it through a bandpass filter
Yeah,
and throwing away everything outside.
yeah, exactly.
And a single antenna or a single telescope, I presume, can have multiple sensors mounted at the same time, or do they have to change them out?
Well, so it varies, I didn't show this one, but there's another array, it's called the Australia Telescope Compact Array. And the way they have it is they have receivers that are on the wheel, so they rotate which one is in focus to be used at different frequencies or whatever exactly.
Multi-band antenna?
Yeah, the GBT does that too, aren't there like 2 or 3 different detectors?
yeah.
Kind of like on a turret?
Yeah, exactly.
They can rotate one.
Yeah, Attica has, I think, like 8 that they rotate in and out. So it kind of, again, each of these, like I showed the components of the one where it's like there's the focus, etc. And they kind of all have the same general design, but there are all these differences between each one about how they actually take observations or process the observations, you know. Little minutia.
Just wanted to point out with the GBT, you don't really appreciate the scale from the picture.
I know,
Just
yeah,
how big it is.
it is pretty huge, I can pull
Yeah,
that
when I
up.
got to the site, and I get there and I look over, I'm like, oh, the heck?
Oh, I think I messed up, Jerry, I went the wrong way.
PowerPoint.
Yeah, cause I think I went to the last slide, and now it's not.
Oh.
Okay. Oh, well, but I think you can pull it up again. Yeah, so right, these are trees, right? And I'm trying to think of what good structure there is. It's a little hard to see, but this structure here is like a little bit of a car park where they keep maintenance vehicles and stuff. So you can see it only comes up to like the foot of this telescope in terms of height. And I actually haven't done this, but they do have days like when they're doing maintenance or whatnot, where you can actually ride the elevator up to here and kind of walk around. There's a little bit of a walkway up there. It's a pretty good, I've heard it's a pretty good view. I want to do that myself, yeah.
That's the place in Virginia.
West Virginia.
West
Yeah,
Virginia.
yeah.
We're driving through there, was I had no idea where we were, what we were doing, right? So we needed gas, so we pulled off in this little side street in this little nothing town. We couldn't understand why it was so not modern, right?
Mhm.
And the gas pumps were the kind that were like right up against
Oh,
the
yeah.
road. And then we walked in, now this is a carload of photographers. I walked in, right? And it was one of these old squeaky wooden floor grocery stores with an old conveyor belt that was, you know, probably run off of a big old huge DC motor.
Yeah.
Manual cash registers, a whole bit, and I'm like, wait a minute, we just like did this step back in time, so we all bail out of the car, I'm like, God, you guys see this?
I know, right, yeah.
Like Trans General.
Well, I was gonna say, there's a town not too far.
Yeah,
from
right
here,
here, right,
And they
like
have,
here.
exactly, well, they have that exact design for their like gas pumps and stuff, yeah, exactly.
Yes, because is that because they like can't have electronic point of sale terminals?
Yeah.
Which of course are known to be very leaky RF.
Yeah, we started to put that all together when we drove around the town and saw the antenna and then, you know, the farms and. Then we did a little Googling, we figured out what it was.
Well, yeah, depending on the camera, right, you can't even necessarily take that into, right, if it's.
Oh, well, you wouldn't there, we just.
But yeah, no, exactly, yeah.
Into the grocery store.
Wasn't it West Virginia that the telescope was built? The dish was built into the earth and they suspended the sensors above it and it failed recently.
That wasn't West Virginia, that's Arecibo. That is, I forget where in South.
Puerto Rico.
Puerto Rico, yeah.
Oh, okay.
So but that was running for a long time, like 10-15 years, and then I think it was some kind of like a crack in one of the supports.
The
or something
hurricane
like that.
account was thrown.
Yeah.
For talent.
Exactly. So yeah, that fell and that was kind of devastating because you know, you only have so many of these instruments, so when you lose one.
But it was really not really being maintained. Cornell was really. I spent about 4 months there myself.
Oh,
We were doing field programmable array multiple channel receivers.
Oh, yeah, okay, awesome. Yeah, there's a new one that they're building or have built in China, that's kind of like Arecibo, where it's just a static dish.
There's no static dish somewhere in West Virginia?
No, not like Arecibo was, no, there's a few others in the same facility that move around like the Green Bank, but not one that's just static.
I remember being there, I was probably a kid, on something, but I saw something that, you know, I always thought was a great new telescope of sorts. But at what station?
It might have been the 300 footer, that was the predecessor. That one-
That's true, cause that one kind of collapsed, right, or something, yeah.
Metal fatigue.
Yeah, so there was a telescope that preceded this one that just had some structural failure, yeah, so they replaced that with the GBT, the green bank.
Okay.
Yeah, I mean, it requires a lot of precision in the whole every aspect of it.
Yeah, it's a lot of work that goes into building and.
Oh, you said part of your research is like 300 to 900 gigahertz.
So, like for radio astronomy,
Yeah.
not so much what I do.
Don't you get, I think that isn't that a region of high atmospheric attenuation?
Well, so that's why Alma is so good for that, because that's on the Atacama Plateau, so 6,500 feet above sea level, and it's also very dry there. So you have very little water vapor, which means you're not really impacted much by that. So one of the reasons Alma is specialized to that upper hundreds of gigahertz range is because of the location. That's another reason VLA doesn't do that. Like few tens gigahertz.
We just have to build.
Because it's much further. Well, you say that, there is NASA's looking at building a moon interferometer right now, yeah, so we'll see if that happens, yeah.
Do you have anything published that Jeremy could direct us to?
Oh, yeah, what's a good way to share that?
Through the Google groups.
Okay, yeah, I can just, I'm on the group for this, so I can just send a few, yeah, sure.
One of the ideas I heard for the far side of the moon was to look at the 1420 megahertz emission from very young galaxies.
Yeah,
So very young galaxies are redshifted by about a factor of 10. So take 1420, divide that by 10. Where does that put you? Right around the 2 meter bands. Right, so good luck finding quiet space on 2 meters. So I think the idea would be to put that on the far side of the moon.
I like to put a repeater there, which still be of use.
yeah, right?
Well, you have to have some way to get a signal around those.
Well, you have a relay station.
Is it, are these antennas affected by the satellite constellations that are flying? I would guess. not,
There's-
Because they're so fine.
Not really, yeah, there are some, they're kind of called chirp signals that come up from some sources. But they know how to characterize and remove those, because that's always at a predictable frequency.
Yeah, it's mostly optical.
Yeah, with like, yeah, what is that, the like chain of dishes that are up there, yeah, we're not really affected by stars.
Because they're a couple gigahertz, right?
Yeah, I mean, I guess the VLA might be, but I think we're a bit above it.
Yeah, they're probably around that range, right? 2, 5.
I would encourage you to write up some of this stuff for QSC. Especially in history.
Yeah, yeah.
Early history.
Yeah, sure, okay,
What if that would be a really good article for the household?
You say,
yeah, alright.
Oh, well.
Do you know if like Green Bank, telescope arrays have like it's like a no-fly zone? Because if a large airline would go over it.
Yeah, they do, so especially Green Bank, Radio Quiet, that includes the sky, you're not allowed to, I forget how it works with the airlines, they're not allowed to fly within some distance. That's true for the VLA and Alma as well. I'm trying to remember if that's true for all of them, I feel like it's not always the case, and they have a sensor that can, like, I know for the ATCO, Australia telescope that I mentioned, compact array, I have used that one. That one doesn't have a no-fly zone because they have a little error message or warning message you get if it detects that there's a plane overhead and you're supposed to like stow it, or just be aware of it, that it might affect your observations, so most of them do, but not all. Depending on like kind of where they are, sometimes it might be too difficult to have them redirect.
Do we have significant radio sources within our solar system? Is Jupiter spinning on?
Jupiter is a bright radio source, that's actually the calibrators I was talking about earlier, Jupiter is a calibrator because of how bright it is. All of this stuff I was showing.
So that's an alternative to WWP.
Yeah, but they give you Jupiter standard time.
Yeah.
So this.
Pulsar is out, yeah.
This emission here I'm showing is from our own galaxy, so like from like molecular or gas clouds within the Milky Way. And then this stuff is like dust and kind of like radio emitting electrons from the center of our galaxy. So yeah, you can look at distant times, you can also look more locally. I showed,
Go ahead.
I was just saying, I showed at the end that protoplanetary disk looking at stars and planets forming, that's within the Milky Way, where that
I would
is.
imagine auroras would be a really bad thing through telescopes for doing that.
It what?
Aurora.
Oh, the aurora, yeah, I mean, none of them are photos. Yeah,
Except for.
there's a
3
few,
years ago.
yeah, right, yeah, so, right, like active solar.
Probably went out in West Virginia, that's for sure.
Yeah, I mean, active solar periods cause more interference for sure. I mean, even back in the early days of radio, they were seeing that with sunspots, right? That's still kind of the case now. So,
A question came up earlier about the satellites as transmitted. They're mostly below 30 megahertz, it's 30 gigahertz.
30 gig, yeah.
Yeah, so that's the lower end. Which by the way, is why earlier in the history of radio astronomy, that was a good range to study because there were no satellites.
right, yeah. Yeah, I mean, the VLA still operates in that range, so the VLA is more impacted by that. ALMA doesn't really.
Well, I'm sure
do
they
that
have that back
at all. Yeah.
Thank you.
Yeah.
This is a great presentation. So if nobody has any other questions or anything, maybe we'll shut down the online here. We'll